Hello YouTube, welcome to Logic 104. So last time I introduced set theory. I've introduced it with axioms, and I said that in logic, if you have a bunch of axioms like set f1, set f2, which we've seen, set f1 was the one that imparts the equal sign with its meaning, and then we have the choice axiom, that these can prove all kinds of statements in mathematics. For instance, they can prove that for all epsilon larger 0, there is an n in the natural numbers, such that for all small n larger than big N, it holds that 1 over small n is smaller than epsilon. This is one of the statements I had in the last exercises. And this is a formula. So a formula is a set of symbols like quantors that we've seen, and terms and functions maybe, and relations that together end in a truth value. So because this quantor is kind of resolved with this variable, and this variable creates a term, and this constant is a term, and then this relation over here is what finally returns true or false. And in this case, it's true within our theory of ZFC, because this relation is a relation within ZFC. And that is sort of how you look at truth in logic and in mathematics in general. Yeah, so we saw that ZFC makes things like sets. We saw it makes the empty set, it makes the set containing the empty set, and the set with the empty set, and this one in there. But I didn't really explain how sets create all of mathematics and why we use sets for all of mathematics. And the reason for this is because sets are really the simplest object that you can make in mathematics almost. It's an unordered list. What is more simple than that? And because it's so simple, it is very broadly applicable. And every field of mathematics, from analysis to abstract algebra to even probability, and every field in mathematics is defined in terms of sets now. And that has been the case ever since the early 1900s, like 19, I want to say. Well, not necessarily. It happened over the early 1900s up until 50 or so. I don't know exactly. Maybe even a bit later. It's quite a new invention. But yeah, so every field of mathematics relies on the same axiomatic structure of ZFC, except for logic itself, which is like looking inside of the cogs of this and other structures to see if there are maybe structures that are more elegant than ZFC. Another thing I skimmed over is I said that the empty set with the empty set is the same set as just the empty set in a set. And the reason for this, if we look at set f1 again, set f1 is a formula, but it's also an axiom. So a formula contains all the symbols that we have in mathematics, and it returns a true value, and because it's an axiom, it is always true. That is, and you don't have to prove that it's true, it's just defined to be true as an axiom. And set f1 was all x, all y, all z, z in x, if and only if z in y implies x equal y. And I said that this imparts the equal sign with its meaning. So sets are equal based on this relation, which returns true or false. And for both these sets, we see that this returns true, and this also returns true. And there's no other thing that you can put here that returns true for this set, and for this set also. So because this relation is what imparts a set with its identity, and because these two sets react exactly the same to this relation, they are equal. And that's why you cannot have duplicate elements in a set. I also have a meme, and I made it in my first bachelor's year when I was learning this stuff. And it actually is incorrect, but it's in the format of the meme, and I thought it was funny. I hope I find it so I can put it on the screen. So since the early 20th century, it has been sets all the way down. But before that, it was actually circles and lines. So you could say that before the logical revolution, before the 1800s till 1900s, in the 1800s and 1900s, there was a lot of rearranging in mathematics. But before that, the axioms, there were only 5 axioms, and they were Euclid's 5 axioms. So Euclid is a Alexandrian mathematician from around 300 BC. They were the most important mathematician in the history of mathematics, I would say, because they are kind of the person who, or group of people who started the whole axiomatic deduction that we still use. And they used axioms for geometry. By the way, we don't know anything about who Euclid was. Euclid used axioms for geometry, so their axioms were things like you can draw a circle everywhere, you can draw a line, you can draw a point at the intersection of 2 lines and a circle. And the 5th axiom was sort of the thing that started the logical revolution, because people were so upset that it had to be an axiom and couldn't be proven. The 5th axiom of Euclid was if you have 2 lines that cross another line, and the sum of these 2 angles are smaller than 180 degrees, then there has to be some point where these lines cross. And that is called the parallel postulate. And, you hear that mathematicians use different words for different things all the time. One time it's an axiom, the other time they call it a postulate. It's not really rigorous. So that's a bit of a history lesson. Yeah, next thing I want to say is regarding relations. So I want to talk a bit about this relation. It takes in a set on the left and a set on the right. All terms in set F are sets. Remember when I said all terms in high school mathematics are numbers? Well, all terms in proper mathematics are sets, except when you're doing weird logic. So when I use a term, usually I will mean a set from now on. So A contained in B. This is how you read this. It is a definition, and it is the following. All x in A, it must hold that x in B. This is what it means for this to be true. And you see that this is not an axiomatic relation. It relies on the in relation, which, last time I did this wrong. The proper way to write this, by the way, is all x in A is actually saying all x in A, and then here I said and, but it should be implies. So this implies x in B. This is the proper way to write this down. But this is a shorthand that you see used all the time. So I'm not going to use the proper way because I want to teach you the standard dialect also. Yeah, so if we look at what this means that you go over all the elements in A, and all of them have to be in B. But if there is one that is not in B, then this relation is false. So let me give some examples. We can draw the two-dimensional plane, which is of course a set, R2. And we can draw a little squibble here, and we can color it in. And we can call this squibble A. And A is a subset of R2, because it's just a little two-dimensional blob in the plane, for instance. So that could be a subset. This one has infinite elements, of course, because there's infinite numbers in this little squibble, in this little blob. And here for this definition, by the way, I used this double dot equals thing again, which means when you see the left thing, write the right thing. And because of this, some people say that this is not really a relation, it's only a definition. But I think that saying that makes everything a lot more difficult to learn and read. Then in that case, you could only say that this is a relation and equal is a relation, but no other things would be a relation, which is just annoying. Also, the same holds for functions. You can define functions. As I said many times, functions and terms can blur into each other, but there is no axiomatically defined functions in ZFC. And that is what I wanted to say earlier. This theory doesn't use any functions. Okay, so now we got all of that out of the way. It's time to learn some set theory. We started with the most simple set, which was the empty set. And then we had the empty set inside of a set. And then the set of the empty set in this one. And we could call this one the number 0, and this one 1, and this one 2. And we can also have this function that maps a set to the number of elements that it has. So this hashtag function counts all the elements. Oh, this has 2 elements, so it sends it to the number 2. What other things can you do with sets? You can take the intersection and the union. These two are important. Intersection of two sets is defined as such. We can define it using the third axiom of ZF3. It's all the x in A for which x is also an element of B. And you can think of it as a Venn diagram. We have the set A, we have the set B, and then the intersection is this part here where they overlap. Secondly, you have the union, A union B. It's a bit harder to define with normal logical language. I think, yeah, you have the fourth axiom defines it, but it's a bit bulky, so I'm just going to say what it does. It's just the set that has both A and B. So if this used to be A and B, then the union is the whole overlapping thingy. And now we can do some basic mathematics. For instance, we can say, let's say we have a set A and a set B, and both of them are finite, so they only have finitely many elements in them. Then we can count up the number of elements in A, and we can count up the number of elements in B, and we can say that the number of elements in A union B, this is not just going to be the sum of the elements of A and the sum and the elements of B, but we also have to subtract the elements of the intersection of A and B. If you understand this, then you understand this union and this intersection and this hashtag. So it's a very useful thing to kind of reflect on if you understand it. Next up in set theory, we have to talk about functions, I think. So a function goes from one set to another set. For instance, we've had the example of f of x is x squared. It goes from r typically to r. So the real numbers, this is just any number, and to the real numbers. But we can also make a function that goes from this set to, let's say, the natural numbers, and it maps this thing to the number 8, and it maps this thing to the number 4. Why not? Right? You can define all kinds of functions. This is just to indicate that you can make any stupid function that you can think of. For now, I want to talk about bijective functions and injective and surjective. If you imagine you have a set, and often when we talk about functions, we draw sets like this. This is set A, this is set B. Set A has all kinds of elements in it, and our function f goes from A to B. Actually, it doesn't go from A, but it goes from what we call the domain of f in A to B. So some elements of A maybe do not have an output in our function, and we are not allowed to write those down here, even though we are allowed to write down the entire set, even if not every element gets hit by our function. So our function sends a bunch of elements in A to a bunch of elements in B. There's a few things that can happen here. One of the things that can happen is that one element in B gets hit twice, by this point and this point, for instance. Another thing that can happen is that some elements in B are not hit at all. However, if our function f hits the entire space B, and sometimes we write the subset that is hit as writing in the entire set as the argument. If the set that is hit by f is the entire space B, we call it f is surjective. I always remember this by thinking it surveils the entire set, so it's surjective. And then the second thing, if for any x in the range of f, so that is all the points that are hit by f, we know that there is only one y in the domain of f, such that f of y equals x, then we say that our function is injective. And I always remember this by knowing that it's not the one that is surjective. So what does that mean? It means that there are no double hits like this one. And this is actually a place where the unique quantifier is useful, although you can also write it without a unique quantifier by saying if f of y equals x and f of z equals x, then y equals c. But this is a lot more bulky than this, because you also need another quanter for the z. So I went over this a bit quickly. Let me re-emphasize what the domain and the range are. This is a dialect thing again. So when I write down a stripe f, that is all the dots that actually get mapped by the function. So these are not in there because the function is not mapping them to anything. Sometimes we actually don't write this and we just assume that the range is everything in the set A, that is. When we write down A goes to B, this is also true automatically because the left-hand side always needs to have the entire range of the function. Or domain. Am I saying range? Oh no. So sometimes we assume that the domain is just the entire set and then we don't write this, and actually this is automatically implied by writing down a function like this, because the left-hand side always needs to have the entire domain of the function. So then these dots cannot exist in our set A. Otherwise our function is not well defined. And so then we don't have to write this here and this, and that might make it a bit more readable. Next up, if I have an element x x in a, and I put it in my function, it's going to map to some y, where y is an element of b. But if I put in a set of elements x, y, or I shouldn't use y again, x1, x2, x3, then this is actually a dialect thing. It's not defined. Functions don't have this generally in their definition, but this is going to map to the set fx1, fx2, fx3. So this way you can map entire sets at once, because in this case x1, x2, x3 is going to be a subset of A, and this thing is a subset of B. But usually you only map one thing at a time with a function. And a second thing about this multiple mapping at once is sometimes these two can be equal to each other. So sometimes the right hand side here is going to be a smaller set than the left hand side. In any case, this is what I'm doing here. When I'm putting a in my function, I mean to ask what is the entirety of the range that is hit by the function. And then if the entirety is b, if every point is hit by some arrow, then it's surjective. And this, again, to reiterate, if no point is doubly hit, so if this doesn't exist, this arrow, then it is injective. A function that is both surjective and injective is called byjective. F is surjective and injective implies f is byjective. What does that mean? It means that f can sort of switch between the two sets and no information is lost. So let me give an example of a bijective function on the real line on R2. Let's take our recognizable example, fx equals x squared. This is not bijective. And we can see that because it goes from R to R. And it looks like a parabola. So this is neither surjective nor injective. Why not? Because if we look at the output point 2, for example, let's say this is 2, then we see that it's actually hit twice. So there is not, if we remember injective, I'm doing first. If we think about what injectivity means, it's said for all x in the domain f of r, there is only one y in the range r for which f of x equals y. That's what it means for f to be injective. And the range here is only the positive real axis, because we cannot reach the negative axis with our function. So f of r in this case equals all the x in r for which x is larger than or equal to 0. Sometimes this is also called r plus. And in this case we can find the square root of the square root of 2 and the square root of negative 2, negative the square root of 2, and both of these map to the same output. So oh, I made a mistake here. These should be swapped. The x is in the range, so f maps to x. Y is in the domain, so it gets mapped by f, like this. So in this case we choose our x to be 2, and then we say there's actually 2, there is an x and a z, y and a z, By the way, if you want multiple quanters in the same set, you can use a comma, like this. There's a y and a z. Normally quanter ordering matters, by the way, in case you're wondering. But if it's the exact same quanter, just with a different variable name, then the ordering doesn't matter. There's two numbers, y and z, that are not equal to each other. Y not equal to z. However, f of y equals 2 and f of z equals 2. Of course, y is then equal to the square root of 2 and z equals negative the square root of 2. So we've proven that our function is not injective. I'm doing these really trivial proofs, by the way, just so you can see kind of how the logical symbols work. Okay, so is it surjective then? Well, surjective meant f of r would have to be equal to the entire set that you're mapping to, R. So it's not surjective, because this is not R, but it is R+. However, if we redefined our function as R to R+, this is a very easy way to make any function surjective if you need. But in this case, we are analyzing it as a real function that goes from the reals to the reals, and it's not surjective. So let's look at a function that is bijective. The most simple function that's bijective is just the function that returns the thing itself. So this would be the function fx equals x. And this is also called the identity. So if you see identity from some set A to itself, it's always the set that sends every element back to itself, which is a function, and it's a function that offers you very little information, but sometimes it's useful. But maybe a more interesting function would be this one, x to the third. So this is actually a bijective function. F of x is x to the third, because it doesn't reach any point twice, and it reaches every point in the real axis, so it maps the real line to itself. Now we've seen a few functions, and now we can talk about what it means for something to be infinite. So we've already seen one infinite set, and that is the natural numbers. And we say that the natural numbers are countably infinite. We can put them all in a row, and we can kind of go through them one by one. 2, 3, 4. That makes them kind of neat. But we can ask ourselves, if we have any set, the set A, and we assume that A has an infinite amount of elements, then a natural question to ask is there some way to compare it in size to the natural numbers? And there is. We do it as following. We say that a set A is smaller than or equal to, and I'm going to use a little squibble to emphasize that this is not the same as comparing numbers, to a set B if there exists a function, there is some function from A to B where f is injective. Why? Well, because if f is injective, then every point in B that f maps to has a unique point in A, so there's at least as many points in A as there are in B. And then we're going to say that a general set is larger than or equal to a set B if there exists a function from A to B where f is surjective. And then two sets are the exact same size if they are smaller than and bigger than each other, or smaller than or equal, or bigger than or equal. And I'm using a squibble again. And that is the same as saying there is a bijective function, because you can combine these two into a function that is bijective with some trickery, which I'm not going to go over, but you can think about how to do it yourself. And this is all by Cantor, who is one of the founders of set theory, still in the 19th century. Some people thought this was ridiculous, but now it's accepted mathematics. So we can use this to compare with the natural numbers here. So if we can make a function that goes from the natural numbers to a, that's injective or surjective or whatever, we have some idea about the infinite size of a, if a happens to be infinite. And now it turns out that the infinitude of n is the exact same as the infinitude of the integer numbers, c, and it's surprisingly even the same as the quotients, but we still have to show that is true. But intuitively it's quite easy to understand, because every quotient is just two integers. So if you have 2 times the integers, then you can make every quotient. And there's a very natural way to make a bijection between 2 times the integers, or 2 times the natural numbers, let's say, and the natural numbers themselves. If you imagine 2 times the natural numbers, or not 2 times, but a cross grid, so it goes on for infinite. Here's the point 0, 0, 1, 0, 2, 0, 3, 0, 0, 1, 0, 2, 1, 1, etc. Then we can kind of create a snaking path through here. And by making this a linear path that reaches every point, we have constructed a bijective function. If we map the number 1 to this point, the number 2 to this one, the number 3, etc. So then we've created a bijective function, and we showed that n is the same infinitude as what we call the cross product, n times n, or n2. And this n2 is very clearly smaller than or equal to z. There are some ways in the construction of these numbers that you can make them, but you can imagine with q it's the same story, because you have sort of 2 natural numbers that go into every quotient. So this one is at least as big as this one, and it's very easy to show that it's also at least as small, so they are the same size. So it might be even more surprising that actually this set is strictly smaller than, I'm gonna use a squiggle again, strictly smaller than, but with a squiggle, the real numbers are. So it's not smaller than or equal, it's strictly smaller. The real numbers are a bigger infinitude than the other numbers. So there's way more of them, basically. Why is this relevant? Well, it puts into perspective just how powerful quantors are, first of all. Because when you're saying for all x in R, you're not just doing what we call countably infinite AND statements, but you're actually doing uncountably infinite AND statements. And uncountable just means larger than n. And by the way, let me prove that actually, that real numbers are bigger than the natural numbers, first of all. And the rest follows by what we call transitivity, which is something that I haven't explained yet. Maybe I should explain transitivity first. No, fuck that. Okay, so imagine that we have a function that is bijective, from the reals to the naturals. We put the naturals here. You might have seen this on Vsauce already. 1, 2, 3, 4, etc. And these are all the natural numbers, and we put them on a little cross table. And here we put the real number that is mapped to this natural number. So let's not even do the real numbers. We're just doing the real numbers from 0 to 1. So if you imagine the real line, that is this little piece of line over here. So let's say we start with 0.13289. It goes infinitely on. And this one maybe it's 9, whatever. So it's every decimal number. And we find some kind of function that maps every natural number to a unique decimal number. I don't know what the function is, but let's hypothetically say that it exists. This is an assumption. We say, assume, if you remember a while back, assume f such that ... This is the natural number, and this is the number that it maps to. So f maps from the natural numbers to the interval from 0 to 1. Let's do the open interval. And we assume that f is bijective. Sometimes we write that with a little squibble on top of the arrow here, like so. This means f is bijective between this and that. So then the only thing we have to do is construct a decimal number that is not hit by our function. So let's take from the first function this thing, but add 1. So we make it 2. And the next one, we take this thing, but we add 1. So we make it 9. And then we take this one, we add 1. So this becomes 3. Let's, this one, 2. Now we come across the 9. So we add 1, but we just make it 0. And this way, we will construct a number that is impossibly hit by our function. Because if this number would be in our list, then you reach a contradiction because you would have changed one of the decimal points of this number. So this cannot possibly be hit by our function. So here we reach our contradiction, and we conclude that so here this was an assume there exists an f, and we conclude there exists no f such that f goes from n bijectively to the interval from 0 to 1. And this is called Cantor's diagonalization argument. Yeah, it shows you some of the weird things that happen in set theory that are a bit alien to the rest of mathematics, but they can be interesting to just kind of think about. And they're a good playground to learn how to use these logical arguments and quantors and such. So I'm gonna make some exercises for you, and next time I don't know if I'm gonna continue logic because I've kind of gone over, there's one subject. I'm going to do induction, and after induction I might move on to abstract algebra because I'm not that good at logic actually. I just know the basics, but I'm a lot better at abstract algebra, and it's also underrepresented on YouTube. So I'm looking forward to that. And I'll leave you with the exercises. Hello everyone, I'm on the move, so I have to do it in a shitty setup. Here are my example exercises. So let me explain what they say. First, here are the ZF4 and a simplified version of ZF3. And I'm just going to quickly talk about these formulas. So a formula can be any string made out of the symbols of the language. So it can have any relation that you defined, it can have any function you defined, it can depend on a variable, it can have all sorts of terms, whatever you want. And it spits out a truth value. So in this case, this formula is compared with this other relation here, with this AND statement. And then the first exercise says ZF4 gives the existence of a set, but not the existence of the unique minimal set. So it says there is some set Z that has X and Y as an element, but it doesn't say if it has maybe another component like W or maybe an infinite amount of other components, right? So it has this redundant W, could have this redundant W in there. How can you use ZF3? And you can use this simplified version to remedy this. So you have to find the formula and phrase the argument correctly so that everything works. Exercise 2. I have a bunch of functions. They go from one set to another set. And then here it's defined what the function does based. And you have to say if they are well defined, if they are injective, if they are surjective. And when I say A over B as an element of Q, it's the unique reduced version of the element. So there's only, for every element in Q, there's only one unique reduced version. So it's not the case that these two are not well defined because this is not uniquely defined. Okay. And then I have a bonus exercise, and that one says, first look up set f8 and find a phi as in exercise 1, because set f8 also has an existence thingy, but not a unique existence. And then once you did test and you find out what the power set is, see if you can find a surjective function from R to the power set of R. Okay, I'm going to give the answers in pause the video, I forgot to say. So I'll give you the answers in 5, 4, 3, 2, 1. Okay, here we have the answers. So say we have some sets A and B. Then by set f3, and these are general sets, there is some big A such that A and B are contained in it, but big A could have a lot of other things. So here I said 3, but I meant 4. Now by set f3, we can make a formula. X is A and X is B. Oh, this should have, when we're defining a formula, we should use double dot equals, of course, because it's not equal to this, because equals is not defined in this context. Okay, you cannot compare a formula with a truth value with the equal sign. Okay, X equals A or X equals B, and then we use this formula with set f3 to prune our set A. We define a new set B through set f3. This existence statement defines it. And B is all the x in A such that x is A, or it's small a, or x is small b. And then we get exactly these two elements, because we know these are both in A. And for every other redundant element in A, this is going to be false and it's not going to be in our set B. And that's how we can make the set with exactly two other sets in it. Okay, exercise 2. So you have to say whether they are well defined, injective and surjective. The first one goes from the quotients and goes to the natural numbers. And it's actually neither. It's a trick question. You would say that it's surjective, because you would say there's a lot more here and you can put every natural number here, but you're not allowed to say b is 0. So 0 is not hit by the function. If we look at what the entire function maps to, it's all the natural numbers except for the number 0. And this notation I never said, but if you have a set and then a backward stripe and then another set, it means this set without these elements, or this other set as elements. And in this case, it's the element 0. So this means the natural numbers without 0. Of course, it's not injective, because 1 over 2 and 1 over 1 and 2 over 1 both get mapped to the same element, namely 1. So the next function, that is this function with the asymptote that you probably know from high school, 1 over x. And it's not well defined, because I didn't say to take out 0 here, and 0 doesn't map to anything in this function, of course. So this one is not well defined. So you can't say if it's injective or surjective. But if we were to define it such that we add infinite to R and we map 0 to infinite, which we are allowed to do, we can just call an element infinite, right, and add it to R. Sometimes we call that R with a stripe above it. Then if we map R to this new R with infinite without 0, then it would be byjective even, because every element is hit once, exactly. We could also make a new unique function where G accent for new unique G. We just add a copy G, but for the element 0, we send it to 0. So we put it here. And then it would also be bijective. So you don't even have to add infinite to it. But in this case, it wouldn't be continuous here anymore, of course. In the other case, also not really, because what does it mean to be continuous around infinite? I also didn't put negative infinite, as you see, and that is quite standard. Usually you only have one infinite, and it just means infinitely far away, whether it's positive or negative. Because, of course, mathematicians, they prefer the complex numbers, and that is a context where infinites get brought up more. In the context of complex numbers, what does infinite mean? Well, you would have to have infinite and a phase to have infinitely far in every direction, right? But there's no really negative place. There is just, so it's easier to think about infinite as infinitely far away in any direction. It's so difficult with one screen to see whether you can see what I'm seeing. Next up, we have the quotients going to the real numbers, and we just do the identity basically, right? So we send them to themselves, but we interpret the quotient as a real number. Of course, not every number is going to be hit here. The square root of 2, as we saw in the last episode or 2 episodes ago, is not an element of the quotient, so it's not going to be mapped here. So this is going to be injective but not surjective. And the way you can think about this function is as the identity, but with an infinitely fine sieve with infinite holes in it, basically. It's hard to think about, but you can imagine it. This one is it's just two sets with one element, and the function sends the one element to the one element, so it's very trivially bijective, but sometimes we haven't had a lot of finite examples yet, so I'm just giving you a super simple finite example of a bijective function. And then the last one is a polynomial. It looks like this one here, and it's surjective, but of course in this little area here it actually maps things 3 times to themselves. So it's not bijective, it's not injective, because there's parts that get mapped to the same value. You can calculate which they are. You can use 0, for example, find where it is 0, and then we can do that very easily. It's x to the 4th times x minus 1, so it's 0 at 0 and 0 at 1. So f of 0 is equal to f of 1 equals 0. So this is no bueno for an injective function. But it does see every element in R, so it is surjective. If you have a polynomial x to the power n plus x to the power, so all of the other terms are lower than n, plus some constant c, then let this function be f of x, then f is surjective, and of course f goes from R to R, if and only if n is odd. And you can think about why that is. Proving this is a bit difficult, but it is an interesting proof, maybe to practice your proving skills if you're interested. Okay, so the bonus exercise I'm not going to tell too much about. You can look up ZF8 if you want. But the last part, this one was a trick question. This is impossible. And I hope you didn't try for too long. But there's a proof that the power set of any set is always strictly bigger than the set itself. So in terms of sets. So there's no surjection from this one to that one. There's a complicated, quite interesting proof for it. I will talk about it in the next video. Bye bye.